There? Okay. A quick poll. How many of you think I went too fast last hour? 1, 2. How many people think I went too slow? And everybody else thinks it's just right. Oh, that's really lucky. Okay, so I'll try to go about the same. Mixture models and the EM algorithm. How many of you know about the EM algorithm? So, okay, so again, very many people. So this is a new class of clustering algorithms which are derived from a statistical model. So now we are going to start by assuming that the data is generated by a distribution, and what we see is a sample from a distribution. However, here again, we don't necessarily try to generalize to out-of-sample results. We just want to describe that. We just want to find a distribution that best describes the data, and then that distribution will have parameters that will represent clusters. And such a distribution is called a mixture density. The technical definition is here. Fk is something like a Gaussian, like a normal distribution. I'm going to call it a Gaussian a lot of times. And so this is a density over R to the power d, our d-dimensional space. And each of these is a normal distribution. They are mixed, which means that the density is a sum with some coefficients, pi sub k, which are called mixing coefficients. And they form a convex combination. This means that if Fk are all normalized and integrate to 1, F will always integrate to 1 automatically. What we get from here, as from the point of view of clustering, is that I get these gamma sub ki, which are the probabilistic assignments. And in this case, they have a very precise meaning in probabilistic terms. They are the probability that X belongs to C cluster K. And they are pi k Fk, which is the probability is the how well model K predicts my point X multiplied by the probability of this F in the mixture and then normalized by F. So this gamma K automatically sum to 1 and also have a very clear probabilistic meaning. Of course, these are classical examples, and many of you may have seen them. This is a mixture in 1 dimension. If you can follow the dotted lines, they show the original Gaussian distribution. So there are 3 Gaussians with centers at different locations with different sigmas as well. And then this shows the mixture density where they have been multiplied by the mixture coefficients. And so they're squished down. This is a mixture in 2 dimensions. The data are 2 dimensionals. And while here I had the density, here I have just samples. It's the 3 Gaussian clusters that you had seen before. In both of them, it's pretty clear visually what I mean by clusters. These will be the clusters. And here, around the peaks will be the clusters. This is also a case where we say that the clusters are overlapping because the density is not 0 in between. So data points here could be generated by by either one of the 2 Gaussians nearby with reasonable probability. So we expect the data points here will be assigned probabilistically to both of these. Yes. Here is not clear. These clusters may be overlapping, but not by so much. Yes. So we expect that a point like this will be assigned with high probability to the cluster that's near. This slide is just an appendix, so I'm going to skip it. How many of you have actually encountered maximum likelihood? Oh, great. Then you don't need a slide. OK. So the maximum likelihood is a principle for estimation. If I have data and I have a model, or sort of a family of models like this F, which depends on some parameters, how do I find the best parameters that fit the data? And maximum likelihood, as most of you know already, says find the parameters that predict the data best. And that's called the likelihood, how well a particular parameter set predicts the data, a particular parameter vector, because this theta actually is all the parameters in the mixture. Yes. And typically, again, very typically, and I'm sure you have seen it before, we use the logarithm of the likelihood. And the logarithm of the likelihood has one of the nice properties of this logarithm is that it transforms the product into a sum, so we have a sum. And inside the sum is logarithm of this other sum, which is cumbersome because I cannot exchange, I cannot put the logarithm inside. Why would I like to put the logarithm inside? Because many usual distributions, many common distributions that we use are actually expressed in logarithmic form or in power form. And typically is the Gaussian, and many of you already know the formula of the Gaussian, I'm guessing here. That has an exponent, and so if you take the log, you get a nice expression, a quadratic expression. That's true of many other distributions, even those like discrete distributions that don't look exponential at first sight. They can be expressed in exponential form, and so taking the log is algebraically convenient. Just to make a parenthesis, taking the log there are deeper explanations why we take the logarithm of distributions, which also relate to distributions that are written in exponential form, because many of them belong to what's called the exponential family models, which is a very wide and popular family in statistics. How many of you have encountered exponential family models? Okay, some of you have. So they're taking the log likelihood has sort of a fundamental meaning, and the log partition function, which is the normalization constant of the distribution, also has a fundamental role. So there are deeper reasons than taking the log likelihood than transforming the sum into a product. Back to clustering by EM. We'd like to find the theta that maximizes this function. And from the point of view of clustering, if we find the theta, then we can calculate the gammas by the formula that we had on the previous page, and so we get what we want as a soft clustering. It so happens, and we'll see more on the next slides, that if somebody gives us a gamma, I can compute the thetas from it too. And therefore, I can always write that the cost of a soft clustering, my L, which is always the cost of a clustering, is the minus log likelihood. It's minus because by convention I always minimize, and for likelihood I maximize. So the goal is to maximize the likelihood or minimize the cost. And how can I do it? Well, nobody talks about it, but I can just do gradient ascent on the parameters. And that, as gradient ascent does, converges to a local optimum of the log likelihood. By the way, I haven't said it, but this cost does not have a global optimum. Or it does have a global optimum, but has also local optima. So it is a hard problem to optimize in general. So we can do gradient ascent that guarantees that we arrive at a local optimum, or we can do what I'm going to talk about, which is the EM algorithm, which also arrives to a local optimum, as most of you know probably. Or I can do something that is more modern and new and has arisen in machine learning, but has been adopted very quickly by theoretical computer scientists. Do a theoretical computer science kind of algorithm, which will not look like EM at all. Or some of them will, but not all. And that will give me a good answer with high probability. Now, the EM algorithm. Again, this algorithm, as all the algorithms that I have talked so far, assumes that we know k, the number of clusters, and also assumes that we start with a random initialization. And as I'll mention quickly before, the random initialization should be done the same way I recommend it to be done for k-means. because it will the quality of the solution depends on the quality of the initialization. And there are two steps, just like in k-means. In one of them, I assign points to clusters. However, now I have a soft clustering, so gamma represents a soft clustering and is the probabilistic assignment that I described before. Note that because all the gammas sum to 1 over k, all the gammas will sum to n over all the data points. So you can think of these little gammas as partial counts. And so if I sum all the partial assignments to cluster k, I get something which is the size of cluster k. This is capital gamma, which may not be an integer, but it stands for the size. And of course, these gammas have to sum to n, the total sample size. And this is just a preamble, because now I'm going to do the m step. And the m step says, well, it's very simple. The probability of cluster k is just the cluster size over n. The center of cluster k is the mean of the points in the cluster, and every point is weighted by its membership, normalized. And at this point, I should have said that my fk this is a mixture of Gaussian distribution. So this is EM for a mixture of Gaussian distribution. If I have another fk, other distributions that are not Gaussians, this m step will look differently. In particular, the mean will be calculated differently, because maybe those distributions will be described by different parameters. However, if I have Gaussians described by mu and covariance sigma, then the weighted mean is the center coordinate, and the weighted variance, again weighted by the degree of membership of each point, is the estimate of sigma. And not to forget, we iterate until convergence. We repeat. Yes?
So what's the f without the k again? Is that just the...
fk is the Gaussian number k.
The one underneath the...
Oh, f of x is a mixture.
Okay, the whole thing.
Yes? So we have to normalize these by the mixture to get this to sum to 1 over k. Yeah? Other questions? Okay. And we optimize over, and we iterate until convergence. E comes from expectation, and M comes from maximization. And the next slides will explain why they are called this way. And then I'll explain that, in fact, they are both, they could also be thought of something else, like projection. Here is one explanation of this algorithm. Let's assume that we have already assumed that there is a mixture that generates the data. And the mixture that generates the data says that for every point, a Gaussian is picked at random, and that Gaussian generates the point with the distribution around its center. Let's assume that I actually know this, or let's embody this in these variables z, I, k, which are indicators. Say, point I was generated by cluster k. Yes? Then I'm going to write something, but I don't know them. However, they can be thought of as random variables. I can write a complete likelihood, which says if I actually know these z's, and this z bar stands for all the, it's not a good notation, but it stands for all the z's, I can write the probability of my data given the assignments, given these z's, which are the unknown, like unknown cluster labels. And then, because I know this z is 0 or 1, I can pull this sum over k outside the logarithm. Yeah. And so now I have something that's much more manageable. I have a logarithm of the likelihood of the point in the Gaussian that generated it, multiplied with 0 or 1, multiplied with 1. So this is another expression of how probable will be the likelihood of the data if I knew who generated each point. But of course, I don't know that. What I know is that the expectation of the z's is exactly gamma k. And again, take it as an exercise. Okay, so if I take expectation, this is a linear function in the z's. Expectation is linear, so I get expectation of z times what's here in front. And I write the log of the product as a sum because I like to separate these sums into two. That's convenient for the Gaussian. That's convenient actually for any mixture because it separates the parameter pi from the parameters inside each Gaussian. And furthermore, it separates the parameters of each Gaussian inside each sum. So supposing that I want to optimize this function instead of the original function, I can optimize the pi separately. I can optimize each fk separately. And as it turns out, EM does exactly this. It optimizes this function instead of the original likelihood. And if you remember what was on the previous slide, if I know the parameters theta, then I can compute these expectations. They are the gammas, and we already know how to compute them. If I know the gammas, then I can always optimize the parameters. And this explains why the first step is called expectation. I'm computing the expectation of these z's. And it also explains why the second step is called maximization, because estimating the parameters now is maximizing the complete likelihood, the expected complete likelihood. So take it as an exercise that maximizing this actually gives me the estimates that you saw on the previous page. Yes? Okay, so I'll show you in okay, so let's say I want to maximize, I want to find the new parameters pi. Yeah? Then these are fixed, and I want to maximize this sum over pi. If you solve this problem, actually this problem is encountered many times. And this expression, and we'll see it in a little bit in more detail, is what's called the Kullback-Leibler divergence. This gamma k is a distribution. And so if you think of putting, so pi k doesn't depend on I. So if I sum over I, I get the big gamma. Yeah? So I get a distribution which is known, and a distribution pi k which is unknown over the clusters. Yeah? Okay, so the distribution that known is this, gamma k over I. And the distribution that unknown is pi. And there is a very short theorem that says that the best pi that optimizes this sum makes the pi k equal to what I said here, gamma k. It's the maximum likelihood estimate for that particular subproblem. And then if I look at these mu and sigma, which are the maximum likelihood estimate for a weighted problem, for a Gaussian with weighted data, this is the maximum likelihood estimation for a Gaussian with weighted data where the weights are these gammas. So if I solve this maximum likelihood problem, I get the formulas from the previous page. Yeah. Are there other questions? Okay. You can do it in two ways. So you can put here I'm maximizing likelihood. But you can maximize a posteriori probability. So you can add a prior, and that prior only influences the m step. So in here, you could add plus logarithm of prior of theta or gamma. That gives you map, and map is not great, but when you have lots of data and the map is over, so in this situation, it's okay to use map. Yes. What you'd like is to sort of Bayesian integration. Or what we will do is estimate for different k's and then choose one. And that we'll do next time probably. Okay, some more analysis of EM. This Q is the expected likelihood. It's exactly the same formula as before, except that now I make it not a function of theta alone, but also of the gammas. So I think of the gammas and theta as two separate variables. And the reason is that in the E step I estimate the gammas and the other one I estimate the thetas. And suppose I want to maximize this function over both variables. Then what E step, the EM will do is to maximize over gamma in the E step and to maximize over thetas in the M step. And if we see it that way, then we can show that in fact this alternate maximization, if we alternate and maximize a single function, then just as for this is the same as for k-means, we are never decreasing the function, so we are guaranteed to attain a local maximum. This is a local maximum of the log likelihood, original log likelihood. And then there are various proofs that when any so there are extra proofs that any local maximum of this function is also a local maximum of the likelihood. Yeah. Another interesting view of EM is that these E and M steps can be seen as projections. In what sense? Again, Zi is just an indicator variable that says which Gaussian generated, which cluster generated point I, but now we think of it as a random variable. So instead of thinking it as knowing it and then computing expectation, think of it as a random variable. And then, moreover, write big X for all the X's and big Z for all the Z's. So now we have a Zi for each Xi, yeah, which is just a number from 1 to k. That's my Zi. And now I write this Q, which is again, it's always the expected log likelihood, the complete likelihood. I write it as a function of the thetas and of a distribution over the Z's. So P tilde is a distribution. What's the probability of the Z's? Before it was gamma, the expectation of the Z's. Now I make it a function of a distribution, so I make it sort of richer or more complex, more complicated. In that case, if I write it as a distribution, I can write the same expected likelihood as the following. This L is the log likelihood, the cost of the parameters. And this part is what's called the KL divergence, or short for Kullback-Leibler divergence. And Kullback-Leibler divergence is a measure of distance between distributions. How many of you have actually encountered it? Great again, very many. Okay, so this is the expression is P log P over Q for any two distributions. And another thing that you need to know is that this is 0 if and only if the two distributions are equal. So this is my log likelihood minus a penalty if P tilde is different than probability of Z given X and theta. Yeah. And the assumption is that there is this big P, P of X and Z given theta, which is just my complete likelihood, written differently. Yeah? So to go back, the complete likelihood is here, but it can be broken into two terms. One depends on the parameters and X with fixed Z, and one depends on this distribution over Z's. And again, it's a lot of writing for essentially doing the same thing, but the cool thing is the following, that if now I maximize over P tilde, which is the same as maximizing over the expectations of Z, of getting the expectations of Z, it's easy to prove that the best, well, it's obvious from here that the best P tilde over all the possible distribution over Z's are the ones that give me probability of the cluster given X, which are my old gammas, if you remember. However, because of this expression, this is the same as minimizing the KL divergence between P tilde and the posterior. And maximizing over theta, you may know, and it's not hard to prove, that maximum likelihood, which is what's happening here, its weighted maximum likelihood, is minimizing KL divergence between a model, in this case is the probability of X given data, and another distribution. So I can write both steps as minimizing KL divergence. And now KL divergence is a distance between distributions. There are other distances that are actually metrics. The KL divergence is not a metric. That's why I put it in quotes. Because it's not symmetric and it doesn't satisfy the triangle inequality. It's only positive and it satisfies the fact that it's 0 when two distributions are equal. Yeah. It's useful not because of its geometric properties. It's useful because it's related to maximum likelihood because of expressions like this. Yeah. However, I can think of this as finding the shortest distance. So from all spaces of distribution, I find the closest to this distribution, which is kind of the marginal of my Q. And here, I find the closest distribution over X that's close to my joint Q. So that's like projecting my big complete likelihood on the space of distributions over X and the space of distributions over Z. And this concept of projection is actually pervasive. It's very wide in statistics and estimation. And I wanted you to see it as an example of that. So basically, we can think of EM as projecting between two spaces. And I will make a little picture, which is the following. Somewhere here are distributions of Z. And somewhere here are distributions. These are the mixture distributions here. So for all k. And somewhere here is my Q, and then I start from this log likelihood, and I project it to this space. I get a point. Now I project this point onto this space of models. I get this point. I project again. Let's try to be perpendicular. It here. And eventually, this will converge to a pair of points, which will be actually consistent with each other, and which will be the local maximum. If my spaces are nice and convex like here, it's a global maximum. In mixture modeling, it's not true. These spaces wiggle all over the place, so they can meet in various spaces. Yeah? So this is yet another view of EM. Now, it's useful to also, going more practical, to see some special cases. For instance, suppose that, and these special cases means that we share some parameters. And logically, what's the most, so we can't share the cluster sizes. Or we could, but it's not so logical. Some clusters can be larger, some will be smaller. The cluster centers, we'd like them to be separate. So what can we share? We can share parameters of the cluster covariance matrices. So this is the formula for the covariance in general. You see the one copied from the previous slide. But now let's assume that all the sigmas are equal. So all the clusters have the same covariance. This doesn't mean they look the same. It means that when I estimate the covariance, I get the same matrix, or the same matrix is good for them. And I'll show you an example. Well, then by parameter sharing, we get a shorter formula. Again, we can say that they don't have the same covariances, but they are all spherical. So no coordinate is more elongated than the other, and then we get this other formula for the covariance, which are simpler. Or we can assume that they are all equal and unit matrix, and then again we get an even simpler formula. Exercises for you, if you have never done them before, do one or two of them to see how it works. It's mostly calculus, really. Another observation is that k-means and EM are really close to each other, and in fact, the k-means is the EM algorithm where the covariance sigma, where distance, so what does it mean that this is the unit matrix? Covariance proportional to the unit matrix means that all distances along all coordinates are weighted the same. So it means we have Euclidean distance. And then it could be any sigma. sigma squared tends to 0, where does it, why do I have to make sigma squared go to 0 or be equal to 0 to get k-means? Can anybody see that or know it from before? Well, that's because if I have two Gaussians, any Gaussian gives non-zero probability to every point. And so in EM world, theoretically, every point is assigned to some degree to every cluster, by a little bit. However, in k-means, every point is assigned to exactly one cluster. And to do that, I have to go have 1 over sigma go to infinity. That will make the assignments hard. This also tells us what we can do with EM. If I want harder assignments, I have to bound sigma from above. So instead of doing maximum likelihood estimation, I put an extra condition that says keep the sigma small. Usually I don't want hard assignments. I'd like the assignments to be soft. So usually I want to do the opposite. I want to keep the sigma from going to 0, because the case when sigma goes to 0 is what case in EM? I heard something that might be right. The case when sigma is 0 is when there is only one point and EM is concentrated, it's putting a cluster on top of it. And sigma going to 0, that's nice because then the likelihood goes to infinity. So it's a really good likelihood. But it's not what we want. So if you see that case, call it a bad run and initialize again. So we can play this, in practice, we can play these games with sigma, bounding it away from 0 to avoid some unpleasant cases like this. We can do more variations on the theme of sharing parameters, and here is a huge table of them with a figure. So we can choose this is a case where all those clusters are spherical, have the same covariance matrix, and it's a unit matrix. Here is a case where all the clusters have the same shape and orientation, so same covariance matrix, but it's not spherical. Here they have different covariance matrices that are all diagonal, so that the clusters are axis aligned, and so on. And there is a paper that classifies them all. More practical issues. What I want to say about the initialization. Never start with k clusters, k centers when you start EM. Use the same initialization as in k-means. And it's not so important that you get the constants right. I'll tell you about an algorithm that tells you what these choices should be. But it's important to start with more clusters, sufficiently many clusters, and do one step of EM with those clusters, and then do the pruning as before. Again, for the same reason that if there are k clusters, you want to have a center in each cluster. You don't want to miss any. Other things that you can do, for the mixture of Gaussians, you have exact formulas for estimating the sigma and the mu. But if you are using a mixture of something else, you may not have an exact formula for estimating the parameters. And in that case, you have to do some gradient ascent inside the M step to estimate the parameters. Because the M step is a weighted maximum likelihood always. Well, that makes the algorithm run much longer. Well, it's not necessary to run the gradient ascent to convergence, or whatever ascent algorithm you're using to convergence, because EM is guaranteed to converge even if you do only partial optimization, so you converge with a very large tolerance, in other words, as long as you always increase Q. So as long as you get a likelihood that's higher than the previous one, you are in business. And you are guaranteed to converge to some local optimum of the likelihood. There is another practical and intuitive reason for not running your inner loop maximization to convergence, and that is that this is only a temporary estimate. You're going to change it in the next step, so why compute it so precisely when it's just a temporary thing? So just make sure that to optimize well in the last step. And in fact, I'm going to come back and say that you don't even need to optimize well in the last step. Does anybody guess why or know why is that? A statistician? OK, I'll leave it for later then, the answer. However, this has a name. It's called generalized EM. As a parenthesis, you can do the same thing in the E step. Like E step is a maximization, as we saw. You can maximize approximately. Now, there is no reason for mixtures to maximize approximately because you have a closed form formula. But the EM algorithm works for other things, like hidden Markov models as well, and many other problems with hidden variables. And in some of them, there is no tractable formula for the E step as it is now. And in that case, one can maximize only to some degree and approximately. OK. Now the third category of algorithms for finding, for estimating parameters in mixtures. And here I'm going to be more explicit than in the previous ones. The computer science algorithms of this category come with guarantees. So they are called probably approximately correct algorithms. And probably approximately correct, let's pack. They come with theorems like that. They say that with probability 1 minus delta over my samples, my estimation is correct, is epsilon close to the true parameters. Yeah? But for the mixture, for the mixture case, we have to assume that there is a mixture. So in the mixture case, these algorithms assume that the data do come from a mixture of Gaussian distributions. And moreover, not every mixture gives you clusters, because you could have two Gaussians that are sort of on top of each other or too close to each other. So this condition, the separation condition, means that clusters exist. So this says that any two centers are separated by a number of standard deviations. The measure of distance is standard deviation. Yeah. It can be generalized to other things that Gaussians, like spherically symmetric, log concave, and other things. But think Gaussians. And what they say is that with high probability, and this high probability is 1 minus delta. So delta is the probability of error, and it's an input to the algorithm. Or it could be an input or an output. So if you give me n, k, d, and this c, which is a separation, I can give you a delta and an epsilon that the algorithm will realize. Or I can find a delta or fix a delta or an epsilon and find how many data points I need to get that tolerance. Basically, with high probability, I'm going to get all the points labeled correctly to their own Gaussian. How can this be possible? Well, it's possible because we are assuming that the the Gaussians are separated. And so each point pretty much with high likelihood belongs to a Gaussian. And the case when it doesn't, it's so low probability that it's inside that delta, the probability of failure. And there are two kinds of algorithms. Actually, probably more than two. One of them is based on the fact, you have a question?
Yeah, just to clarify, the C has to be greater than or equal to 1, right? Like it has to be at least a standard deviation, or is there any restriction on that?
Oh, we'll see what C is. Actually, worse than that. Is something that depends on dimension. and so on. So it depends on dimension, like d to the square root of the dimension or the d to the 1 or other things, for this to hold with good probability. OK, so what do they do? Again, we are assuming that the clusters are separated. Think of them as pretty far. Well, I'm going to project the points on the principal components and project the points on that. So in the hour before, I said never rescale the variables because then you change the clustering. Well, projecting on a subset of the projecting is a way of rescaling the variables, and actually quite brutal. Some dimensions go to 0. And others are preserved. So projecting doesn't elongate anything, but it squishes to 0 some things. So why is this good? It is good because, as I said, if the clusters are far enough, then the principal subspace will be the space. So suppose these clusters are spheres in 3,000 dimensions. But if I look at their centers, 3 centers define a plane. And if I do principal components and I have enough data, and they are far enough, by principal components, I'm going to get exactly this plane of the data where the centers are maximally separated. Yes? So although it's a 3,000 dimensional problem, if I have k centers and they are in general position, it's a k minus 1 dimensional problem. That's the first observation, as long as the clusters are round and nicely behaved. And then after I do that, well, they have a complicated way of harvesting the clusters. Harvesting means that I'm assuming that this cluster could be large. It could have a larger sigma. And this will be smaller. Or some of the clusters have fewer points, and some clusters have more points. And so they look at various things like inter-cluster distances and slowly construct a region that contains all the points from the cluster. And then after they eliminate the most salient cluster, which means compact, they take all the points out and go and find another cluster that's salient. Yeah?
Can you explain what you mean by the k principal subspace?
Do you know what principal component analysis is? Yes. So that's it. You do principal components, and you get the kth principal subspace is the result of principal components with k components. Yeah. So you take the covariance of the data, and you take the principal subspace of the covariance matrix. That's what it is. Yeah? Yes. Actually, it should be k minus 1. It's a typo there. Yes, I have 3 clusters. I wanted the 2-dimensional subspace. Thanks for asking. OK, so basically, and here is where I say that the covariance of the data represents actually the geometry of the cluster centers and has nothing to do with the covariances of the centers. Or usually doesn't, especially when there are clusters in the data. OK, and then the harvesting is done so that you can prove the result. Another algorithm. There are other algorithms that say, previous algorithms that say we don't have to project the data because we know that if these the Gaussians are in high dimensions, we can find the probability, we can find the distribution of xi minus xj. And in particular, if we can find in high dimensions, if we find the expectation of this distance, what's the expected distance between 2 points coming from the same Gaussian? Whatever that is going to be very concentrated around its mean in high dimensions. So with very high probability, all the distances will be around the mean. And so there are other algorithms that say, I'm going to look for the very small distances, and that will give me an idea of what's the sigma of the smallest cluster, of the cluster with the smallest variance. And then progressively, I'm going to create a core here of things that points that are close by, and I'll find the center. And then after I have an approximation for the center, I can actually cut out all the points that are in this cluster. And then I repeat for the next cluster, and so on. This is theoretically not as good as projecting on the on the subspace, on the principal components. And in fact, projecting on the principal components is a good thing to take home. Together with the previous initialization, is one of the best practical things you can do. Yeah.
So when you do the principal components, the eigenvalues tell you anything about whether or not you can get K? So if you get your PCA, if you take an arbitrary K and you take K minus 1, and your K is too big.
Okay, so the question is, it's an interesting question. He says, shall I look at if I do principal components? And if I look at the eigenvalue, does it tell me that K is bad? Not necessarily, because it may be that, the worst case is when these are on a line. Then the third eigenvalue is very bad. Yes, it doesn't tell me anything. But if they're a little bit along a line, then it doesn't mean that K is bad. Very nice question. There was another question in the back? OK. But then here is the algorithm of Dasgupta and Schulman. And actually, if I didn't even give you that. No. OK. Tomorrow. Because that's important. OK. So another algorithm, which says the following. Suppose that I have these clusters. And they are in very high dimensions, so they don't necessarily point at each other. They're all in very high dimensions. And they're still separated pretty OK, because they don't point at each other. In 2 dimensions, this would be very bad, because this Gaussian will account for points here. I hope you see that. But in many dimensions, no. What can I do to make the problem easier? Well, I'm going to actually project onto much lower set of dimensions. And why is that? Because there is a theorem that says that, and it's easy to prove, that says that if I project a distance on a random direction, if I project a vector in very high dimensions to a number of dimensions that's not too small, up to a point, the length is preserved with high probability. And what do I want to preserve? I want to preserve actually the vectors that represent the cluster centers. And so if I project the Gaussians on lower dimensions, like from 300 to something that's k log k dimensions, then that means that these points will be squished together. Like points inside the cluster. With high probability will be squished together and will be all here. And these will be squished together and will be sort of around here. And these will be squished around here. But if I look at the distances between clusters, most distances, if I have k clusters, most distances are between points in different clusters. Yes? Only a small number of distances are inside. Those are preserved with high probability. And so if I project on the right number of dimensions, I preserve the large distances and I squish the inside cluster distances. But I don't care. I like to squish those. Yes? What I don't want is to squish these to 0. And with high probability, this won't happen. Moreover, another nice thing happens. If the clusters are not Gaussian, and I project them on lower dimensions, they will become more Gaussian. Does anybody see why or know why? This is actually a well-known fact. OK. What's a projection? A projection means on a plane means that my x goes into some of goes into wx, where w is a matrix like this. OK? And so it means that every component of x here is sum of wi jxj. This is yi. Yeah? Well, assume the x's, xi's, xj's are random. Yeah? then what do I have here is the sum of random variables. If they're independent in any way, and most of them will be with noise, by the central limit theorem, y should be Gaussian. So even if I start with clusters that are not Gaussian, if I sum enough of these, I get something that's approximately Gaussian. And that is the powerful idea in this random projection paper. Yeah?
Is this discussed somewhere in one of these papers?
Yes, in the Dasgupta 2000. Yes. So this paper is about random projection. This is about harvesting. And this is also about harvesting. It's sort of, actually, no, that has some, that's another principle, but it's enough of, there are plenty of good ideas. So each of them has a different idea. That's why they are all three there.
And in one paper, they show that you can actually, that clusters become more Gaussian in the projection space?
Yes, in the one in 2000. Actually, that's very well known. If you know projection pursuit, for instance, there you project on sort of, projection pursuit, you look at a projection that's interesting. And the definition of interesting is it shouldn't be Gaussian. So if you take a data set and project it on some direction, and you look at what you get. If it's Gaussian, you throw it away, because that's what you expect to get. If you see groups, that's an interesting direction to look at. You found an interesting dimension of the data. But what these other papers say is that for clustering, you can do it with PCA. You don't have to search for the projections. Many times you find them easy. Like in many, if the clustering is good enough, you find them easily with PCA. Other questions? Yeah.
How do you find this low dimensional subspace? Like LDA?
A principal component analysis finds it. Approximately. OK. And it's a good time to, next time I'll tell you about another algorithm, but I want to have some slides for it. And apparently they are not here. Here's an example of what can be guaranteed. And this is one of the best algorithms in this area. It says that the centers have to be 4 sigma times something that if you go through has a k. So approximately 4k sigma. That's pretty far away if k is large. So what's good about this? We have theoretical guarantees. We know that if we have Gaussians that are separated, we find the clusters. There's no messing with local optima. You run it once. They're not very expensive, these algorithms. You find the result. They are good ideas for other algorithms. Like they could be used as initialization. However, I'm not sure this is on a slide. There is a problem with these algorithms. And we can talk about it tomorrow too. They seem to make, and they pay a cost for this. The cost is in this very, very unreasonable requirements. They seem to make the following assumption. The theorem says, so what's wrong with this theorem? It's that the algorithm finds the true labels. So they guarantee that you find the true labels for every possible point. Now, this is statistics. You shouldn't be trying to find true labels for every possible point. You should admit some error. Yes? And therefore, because they want to find the true labels for every possible point, their Gaussians have to be really far apart, so that no point flies to the other Gaussian by mistake. Yes? We don't need something so strong. We only need to make sure that if the Gaussians are separated by something reasonable, we are going to make as many errors as no more errors than what the theoretical overlap between the Gaussian is. And that's all. However, interestingly enough, and because you are researchers, this is a research problem. Nobody has I don't know of any result that tries to set this theorem. I don't know of any result that says, I guarantee an error no larger than this much in this framework. OK, and on this note, I'll stop and take questions, if there are any. OK, thank you then.